Okay, so we live, we back. Hello. So hello again, welcome. And let's continue problem solving. All right, here we go. Here we go, H index 2. I spent a little bit of time watching another one of these interviews, and oh boy. Oh boy. What do they call that? One of the, oh, this might be just a repeat of the previous question. Yeah, the video I was just watching is, oh boy. Anyway, unrelated. So we'll leave it. Given an array of citations sorted in ascending order, each citation is a non-negative integer of a researcher. Write a function to compute the researcher's H index. According to the definition, we're just going to say a scientist has index H if H of his or her end papers has at least H citations each, and then we'll just leave the other ones. Leave the rest of the definition because it gets confusing. 0, 1, 3, 5, 6. 0, 1, 3, 5, 6 means the researcher has 5 papers in total. Each of them had received 0, 1, 3, 5, 6 citations respectively. Since the researcher has 3 papers with at least 3 citations each and the remaining 2 with no more than 3, her H index is 3. So basically, H index would be if there's H papers with at least H citations. And we just solved this a moment ago. One way of doing this is if it's already sorted, you can just loop from left to right and take at each index, if you consider the number of papers to the right, all of those papers would have at least whatever that number is at that index, whatever that value is, all those papers to the right would have at least that much, that many citations. So you can take the minimum of that number on the numbers of papers. The minimum of that number is a possible H value to consider, and then just compare that to the your current H value and take the larger of those two. That's it. Do that. So if it's already sorted, you can do that left to right. So it would take linear time. Now, what's interesting though is they're suggesting there is an added interest part of this. So there's a way to do this also if it wasn't sorted in linear time, where obviously you could sort it and then do the same thing, but you can actually create a frequency map hashing all of the numbers to their respective places and all the numbers that go outside of n, right? So each value would be its own index. So you can count the number of papers with a particular index, and then all the papers that are greater than the number of papers total, all of those would just count as, because you can't have obviously it's fixed how many papers you have. So that's the largest possible value you could have for your H index. So all the papers that were cited more than that, basically you just throw them all into the same bucket. And so you have like sort of a modified version of sort of I guess a counting sort type of thing. And then you can walk from back to the front to get that cumulative amount of how many papers have at least as many citations at each index. Yeah, and then so you can get that sort of. So the other number that would be similar to would be the sort of number of citations to the right. That's sort of this cumulative from the back, accumulating the numbers of papers would give you that kind of that same kind of number. And so you just take the minimum of whatever index you're at, the total accumulated number, and then whatever the minimum of those two numbers, compare that to whatever your current H number is, and then return that. Take the larger of those two. So that's what I know up to this point. Now there's apparently a way to do this. Apparently you can do it in logarithmic time complexity. So we can just go ahead and code up the, excuse me. Just code up the solution that I know works. Excuse me. Excuse me. Or just vowels left. And actually, you don't even need, you can just put that right in there. Right, I think that does the trick. What? Wait, what? Oh, so it's not I, it's citations of I, the value there. What is the what? What's going on here? Oh, I think I'm missing. No. What? What's wrong? What? No matching call function for call to min. Oh, unsigned along? Interesting. Really? Huh. Alright. Well. It's a little weird. Okay, let's go for it. All right, there you go. So that was strange, but yeah, I guess that has to do with the. This is technically an unsigned along, I guess. I don't know. That's odd, but oh no. But okay. The interesting part of this though isn't that solution. The interesting part is. Can you solve this in logarithmic time complexity? Whoa. Whoa. That's a lot more interesting of a question. Really? Interesting. Well, I guess you could. So what you would do is obviously each value has this, right? Each index I has an h value, right? A possible h value. And what's interesting is that from left to right, your h value actually increases. So each of these numbers, believe it or not, are actually in non-decreasing order from left to right. So, or rather, I shouldn't say this value. I should say this value compared to sort of what you already see. These values are not necessarily in non-decreasing order, actually, because it could be those numbers could be all over the place, but what your h value is sort of is non-decreasing as you move from left to right. So I wonder, well, basically, the problem with this is that you assume we know, like, what if you just did, That's a good question. Can you do it logarithmically? All right, I gotta think about that some more now too. Oh no. Oh no. The problem with that question is the problem with that question is oh, excuse me. Oh. Excuse me. Yeah, this would be trivially easy, except the problem is that even though, we have that potential h value to consider at that point, we need to know what the previous h value is in order to get the right h value at that point, because the because the previous h value might be larger than the one that you're considering now. Now, something kind of interesting is that the number of possible h values, right? Like you can only have from 1 to h for your h value, right? Or 1 to h, rather 1 to n. So yeah, you should be able to do, I believe you can do this logarithmically. That's interesting, really interesting question, man. I wouldn't have thought of that either. Hadn't been prompted. Couldn't even imagine that. So the reason why this you can, I believe, is because the set of numbers that you have to work with is pretty small, right? It's only from 1 to n possible numbers that you could have. I want to say that you can do you can actually binary search over the h values, if that makes any sense. You could test to see whether or not that particular h value is even possible. So how would that work? All right, so you would say, okay, so is your h value larger or less than or greater than, let's say n is 5 or n is 10. So is it greater than or less than 5? How do we know if it's greater than or less than 5? Well, you would look at index 5 Is it index 5? Yeah, I guess it would be. I guess you'd have to go. You'd have to go. You'd have to look between index 0 to 5, right? Because everything to the right is going to be larger, greater than or equal to whatever number you have there, right? So if you could actually perform a logarithmic search. So yeah, I think so. So I think you do 2 logarithmic searches, and this is trivial. So you say, okay, is it greater than or less than 5? So do a logarithmic search on your sorted array to find the first position that's greater than or equal to 5, and you can tell whether or not that index, you can get what that possible H value is. If that is also greater than or equal to 5, then it's true. If not, if that first number, if that index is too far, then it's false, right? And then now you can split on now your answer. That logarithmic search gives you the answer to that question, right? I want to say this is actually log squared, though, because it would be 2 logarithmic searches. It would be a logarithmic number of logarithmic searches, if that makes any sense. Which is actually log of n squared. It's not quite logarithmic complexity. It's actually a little bit slower than logarithmic, which is interesting. Well, actually, maybe it doesn't have to be logarithmic, because if maybe the search itself could be maybe the query doesn't need to be logarithmic. So if you look flat out at that index 5, right, and you say, okay, what's the number there, right, or just 10 minus 5, right? Because everything to the left of it's going to be smaller, you don't need to look to the left, right? Because if it's greater than or equal to, if that number there is greater than or equal to 5, then you know it's true. If it's less than 5, then it doesn't matter the stuff to the left, because even though you have more I guess values to consider, those numbers are smaller anyway, so it doesn't matter. The minimum of that is just too small. And the values to the right, they're all going to be greater than, but it doesn't matter there because you don't have 5. So you can actually just look at that index directly. So you could do that in constant time. Oh, that's super interesting. Wow, that's so clever. That's so clever. So here you go. I got it. Got the answer. You ready? Logarithm. Yeah, you can do it you can do a binary search on the. Yeah, watch this. Watch this. Hopefully I can code this up properly. Int a equals 0, b equals citations dot size. Right, and just thinking, yeah. So it goes. Citations. I'm just thinking it could be 0. Really, it's size minus 1, the index minus 1, right? Hold on. I just want to get it right. So the index we're going to be looking at is something like, I'm sorry, I just have to think about this for a second. Because the ranges don't quite line up the way that I'm expecting it to. So like if you had from 0 to 10, if you had 10 papers, the indices are from 0 to 9. The logarithmic search though actually is going to be from 0 to 10. So let's do it that way. Let's think about it that way. So the loop is going to look like the following. While A is greater than B, we'll say int mid is going to be A plus B over 2, right? Yeah, that should be fine. And we'll say if there's an if and an else, right? So there's sort of a ret equals 0 we'll start with. I want to say we're going to operate on the indices themselves. Hopefully that makes some sense. Okay, so we have this mid, A plus B over 2. It's, no, I don't know. It's a little confusing. We'll do it this way. So if, basically we want to say if mid is a possibility, right? So at citations of mid, if, see, that's the part that's confusing. It's we're gonna loop. How does this work? Okay, no. We're looping over the possible numbers from 0 to 10, right? That's the binary. So binary searching over that range. Stick it right in the middle initially, right? And we say, is it greater than or equal to that number? If true, then we look to the right. If false, look to the left. To tell if it's greater than or equal to that number, if h is greater than or equal to that number, we're going to take a look at that number. We actually want, here's the part that's confusing. Hold on. We actually want n minus I for some I to be greater than or equal to mid. So it's n minus I greater than or equal to the mid. We'll call it m, which means that I, and actually that means that is it greater than or equal to m, which really we want the smallest possible I, or the largest possible I, right? We want to move all the way. The largest possible I. We want to move as close. We want to get as close to m as we possibly can. So we actually want n minus I is equal to m, which then is to say that I is equal to m minus n, or n minus m rather. I is n minus m, which is very confusing. Yeah, I think that's what I'm getting kind of hung up on. And then we want to say, okay, you get the value, you get this number, the minimum of citations of mid at that index of I, really, and n minus I. Which is, it's not the same thing as mid. That's the key. N minus I should be mid, I think. If mid is 5, is 0, 1, 2, 3, 4, 5, and n is 10. 10 minus 5 is still 5. So and it's going to be 5, 6, 7, 8, 9. We still have 5, right? Still have 5. This is just mid though. This is really n minus I. So this minimum, if this is greater than or equal to mid, that's what we're looking for. If this value is greater than or equal to mid, and actually, we don't need the minimum of these. We already know mid is large enough for what we're looking for. So really, it's just if this is greater than or equal to the minimum, the mid that we're looking for. If that's true, then we can update ret to that value. So we look to the right, update to that value, and then we would continue updating to that right, to the right side, which is A would be set to mid plus 1, and B wouldn't change. Continue to go to the right. Otherwise, we don't update ret. We go to the left, and we say A doesn't change, but B becomes mid minus 1. Yeah, a little confusing. But if that value doesn't work, then if that value works, then we're going to continue going down the right side, update our point. If it doesn't work, we're going to go down the left side. I don't know, man. I've always had a hard time with binary searches. Like, it's hard for me to manually. Like, I wish I could quickly code up binary searches, but like I'm always slow. Like, it's already been like, I had the idea a while ago, but it's already been like 10 minutes of just like trying to figure out. Yeah, I guess we do have this ret value that we have here. I think that's it. Something like this. I don't actually know. Wrong answer. Nice. Okay, so 1, 2, 3, 4, 5. We have 5 values. We say, okay, we say, okay, 5 values. 5 divided by 2 is the third. We end up the third position here. 5 divided by 2 is 2. So we're looking for if mid is greater than or equal to, if this value, which is 3, is greater than or equal to 2. So the midpoint is 2 we're looking at. And it is. Now, this isn't really correct, right? Because n minus mid, we said the mid is 2, and mid is 2. N minus 2 is 3. I is actually 3, so it goes 0, 1, 2, 3. I'm very confused. I think I got the math wrong. But we want whatever this midpoint is for 2, we just want, yeah, we actually do want 3. That's actually correct. We do want this, yeah. And red is at least 2. Yeah, you do have at least 2, right? This value is 5, right? So why do we get 0 though? Why? What? I'm so confused. What is going on? Oh. Right. This probably also has something to do with it. Oh, okay, got the right one. All right, I was like, what is going on, man? I'm so confused. Thought I had the right logic here. Just throw some test cases in there. No. This took me a while. Runtime error. Which one? Okay, got that one correct. That's good. This one. Also correct. Sweet. How about this one? All these zeros creates a problem somehow. Heap overflow, buffer overflow, huh? Okay. What happened? So 0, 1, 2, 3. Midpoint is it's 3. It's 4. So 2. So 0, 1, 2. Set I to 4 minus the midpoint, which is it's at 2. So 4 minus 2 is 2. So it should be 0, 1, 2. And then, so this is the first spot we look at. And we say citation, so that's false, right? So we said B equal to the mid minus 1. So I don't touch A, but we shift B. So mid is 2, B is now, it's going to be 1. So 0 and 1 we look at. And we say, okay, 0 plus 1 divided by 2 is 0. So look at index 0. We say so that's what we're gonna look for now. So we went from 2. We're looking for 0 through 4 for the possibilities. Now we're looking for 0 through 2. We ruled out 2. So we're actually 0 through 1 now are the two numbers we're gonna look for. We say start with 0. If 0 is citations of 0 is a 0 greater than or equal to mid, which is 0. It's true, so we set this to 0, and we set A to increment A to 1, right? So now we're looking on the right side, so now we have, it should be A is 1, and now this is the midpoint plus 1. B is 1, A is 0, mid is 0, mid plus 1 should give us 1, so this should be 1 and 1. Now we say, oh, I want to say, that's probably what we have to do. No? What do we do? A is 1, B is 1, red is 0, I is, so 1 plus 1 over 2 is 1, n minus 1, n minus 1 is 0, 1, 2, 3, 4, 4 minus 1 is 3, 0, 1, 2, 3. Oh, what? How it happened here? How come we ended up over there? What is going on? Wait, whoa. What? What? Uh-oh. Wait a second. I is n minus mid. I'm so confused now. When the number we're looking for, when this is 1, oh, I'm really confused now. So just say initially we don't go to the right. What is I? This is so confusing. This is so confusing. I is n minus the number of papers that we're looking for. So basically this index will give you from left to right the number of papers that you need. And basically n minus I should give you mid. That's what you're looking for, right? So if I is n minus mid, then n minus mid is the correct value for I. That's the right index. So if our mid is, if A and B are both 1, that means we're looking at just 1, right? To see if we have just 1 paper. The right index to look at is, really could be any index. Oh. But actually I would end up putting that all the way to the right side. Oh, I see the problem now. Oh, that's interesting. Huh. Yeah, you run into a bit of a problem, don't you? Run into a bit of a problem, don't you? The index that I'm looking at is here. It's way over there. It's in the wrong spot, basically. And it's actually fine to look at that index. Because it actually should be 3, I think. Index should be 0, 1, 2, 3, which I think is the index you get. N minus, so the mid is 1, n minus 1 is 4 minus, yeah. So it is all the way over there, but it's false, it's 0. So that's pretty interesting. That means, okay. So I think part of the problem is like how I'm thinking, like I said, how I'm thinking about it's not quite right. You got to kind of separate. You're searching in like the queries that you make into the array is different from the range of search values that you're operating on. So the binary values that you're operating on, you're just using the array to perform a Boolean evaluation, and the index in the array. The range that you're operating on should not actually be applied directly to the array, which is really confusing. I think that's why I'm getting so hung up on this. Right. I think this is still right though. Like I don't know why this is wrong. So what that means is, okay, so you have from 0 to 4 in this case. So you have from 0 to 4. 4 divided by 2 is 2. Now you're going to say, okay, is 2 a possibility? So you check at the index to give you 2 papers, which would be index 2 here, and you see that it doesn't work out, right? This value is not greater than or equal to 2. So now you say, okay, so this is false. So now we don't modify the return value, and we say, okay, let's check. Let's now move our range from 0 to 4. We excluded 2. It's gone. Like we can't get 2. So we got to go to 0 to 1 now. So B is now 1, A is 0, and now you say, okay, add these two together, you get the midpoint is 0. Yeah, it's basically A is 0, B is 1, 0 plus 1 divided by 2 is 0, and then this is actually why we're getting an issue, because I being n minus 0, 0 is always a possibility, sort of by default, but we don't need to check 0. 0 is just true by default. So actually, we shouldn't even check 0, I think. Right? Doesn't really make sense to check 0. That might be why we're having problems. Really doesn't make sense to check 0. Yeah, okay. That makes a lot more sense. Because what you would do, you would just exit this loop at some point if it's 0. You really only care if it's 1 through n inclusive. And the reason why you have run into problems is that this I value, this query gets kind of funky. But obviously now if we do it from 1 to n, then when we add A and B together, we would have 1 to 1, and then you would get mid is 1, you have n minus 1 for I. You check the last paper, see it's a 0, say, oh, that's not true there either, and now the mid drops off. That B value drops below 1, and then now A and B are not equal, and then you can exit. Okay, yeah. I think that's sufficient. So let's try some other test cases that are kind of interesting. See if we get anything funky going on. All right, let's give it a shot. Nice. Okay, interesting that after all of that, even though this is logarithmic time, it's still about as fast as the other. Still about as fast as the other solution, which is kind of funny. You have to have a lot of numbers for it to be really fast. Yeah, that's actually really annoying. I'm kind of annoyed now. That took me forever to write too. It took me forever to reason through it, to reason it out. It's such a simple thing too. I'm so annoyed. I'm so annoyed. I feel like I did so well. I figured it out. I realized it, and coding it just took me forever. I guess this is kind of a special problem, because this query is like really unique thing. Like the whole thing is very unique. Obviously this is logarithmic. Because you split this range every time you yeah, pretty interesting. I don't know, man. There's something about writing the custom Boolean searches that I like. You could like how would you just employ like standard upper bound for this? I want to say that you can't, but it's like you're looking for you're looking for the largest value between A and B, where this query is true. This n minus mid, this n minus value is greater than or equal to that value, right? It's like you're looking for the largest value where that's true. How would you even do that? I think you can. I think it's possible. It's just. Oh no, that's not what I'm looking for. I got tricked, man. I got tricked. So I was looking for. There's a value. It's not really a value you're comparing against. Greater than value or less. No such element is found. Yeah, I don't know. Really interesting this routine, but like what you're looking for is kind of special. It's like it's not quite just. It's actually like. I want to say it's like a minimum or a maximum. Like it's a little. I don't know. I'm not sure how I can use like a gerrymander that in there. The upper bound function to do a logarithmic search. It would be like if you took every number and converted them using this to true or false. And then I guess what you're looking for is actually, it's really just true or false, and you're looking for from left to right. I guess it would be in these numbers, it would be the largest value that's true. So it'd all be false, but it's the greater than false. So let's do the first value that's greater than false. Let's try it that way. Let's try it that way. Right? You ready for this? It's going to be, and the range of values is actually we're going to loop over these numbers. We really don't care. We're going to use I don't know, we do care actually. I want the indices. See, that's the other thing too, is the iterators themselves have to be, they're just indices really. Not even indices, they're just numbers, just ranging over a great range of numbers. I don't want to it kind of defeats the purpose if you regenerate all the numbers to loop over. Basically the data to work on. Yeah. I mean, technically you can loop over this, and then just each number you consider it as sort of like add 1 to it. The result, if that makes any sense. So you could try something like this. If you could try that. So it would look like this. Standard upper bound. First you have this auto comp. Looks like this. Does some things. And you have type 1, type 2, which is just basically an integer. Now, you need the index of these. I don't necessarily want the values themselves to consider. I want to consider actually the indices of these. No, it won't work. Because these are values, right? These are actually the integers in the array rather than the indices of the array. So I think we're kind of stuck with a custom version of it. Yeah, this is really neat, this function, but this is a case where it's kind of awkward to try to fix that in there. Yeah, anyway. All right, pretty interesting. Let's look at the solution, see what it says. Oh, it's premium only. All right, we'll leave that. We'll leave that. I don't want to give away answers that they're trying to make money off of. That's not right. That's not right. I think talking about this stuff is fine, but I don't want to do that. I don't feel right doing that. Technically not even supposed to see this problem without premium, but I mean, like, what is it? Your fair use, if you're going to talk about it, you know, for educational purposes, I believe, which is what this is. And then the other thing is, what do you call that? I think that's it. It's really just fair use. I think that's it. Yeah, these aren't like super hard questions that, like, you know, it ruins it for other people if you don't know the answer, if they give away the answer. That's not really. But if they put like, you know, a lot of effort into like writing a nice solution, then I kind of, yeah, it doesn't sit right with me to, makes me feel like I'm stealing it if I talk, you know, I show it, talk about it. I don't know. Something about that doesn't sit right. I think it's probably also protected by fair use. I don't know. But anyway, I don't know. I'm not gonna get too hung up on all that. But obviously, if they were to ask me to stop with this stuff and to remove the videos, I would do it. You know, I don't think I need this stuff up here. I just like to talk about these things. Anyway, so yeah, that's logarithmic. I couldn't think of a way to use the upper bound to write the solution in logarithmically, like in like just a few lines. Like, it's kind of tricky to do that because you're not really iterating over. Yeah, the thing that you're iterating over is like just the natural numbers, I guess. You could, I guess, does that exist? Let's try to see the ones. Does that exist? Nah, I don't think it would. Alright, anyway, let's not get too hung up on this. This is like a very specific kind of use case. I think you really wouldn't it would be kind of challenging to find like something from the STL that like perfectly fits this, because you pretty much always, if you're going to iterate, if you're going to binary search something, it's almost always over some range of elements. You know, it's usually, very rarely is it like an abstract iterator that's not even really connected to anything underneath, which in this case, the values themselves that are derived from sort of the problem, I guess, and the array, that's actually what we're binary searching over, which is like sort of a layer of abstraction above, which is a little weird, but yeah, pretty interesting. I like these questions. These are good. Let me end the stream there. We spent a lot of time talking about this, almost about an hour, so I think it's time to just say, you know, thank you all for watching. I appreciate it. I will talk to you soon. Have a good rest of your day. I'll go ahead and end the stream here and take a break. Maybe go make some food, maybe go exercise. I don't know. I kind of don't want to exercise today. I'm like nervous about it, if that makes any sense, because it's kind of like a public gym, you know. So I'm like, not too many people use it, but I'm like hesitant to go use it just because there could be other people there. And anyway, let me go. I'll talk to you soon. Have a good rest of your day. Thank you for watching. And what else do I have to say? I don't know. I guess that's it. Yeah, I guess that's it. Probably end stream here and then figure out what I want to do next. So I'll do that.